welcome you. Have you ever found yourself picturing AI as, something straight out of a sci-fi movie, maybe conscious machines, perhaps even with their own agenda?
Yeah, it's a really compelling image, isn't it?
Totally. But often the reality behind these incredible systems feels well, a bit like magic. So today, we're pulling back the curtain on that magic.
Indeed. And what most people perceive as cutting-edge AI is really, at its core, a sophisticated application of mathematics.
Right. Not some mystical force.
Not at all. AI is actually built from these intricate systems of equations, optimizations, probabilities, and high-dimensional geometries. So our mission today is really to demystify AI by exploring the robust mathematical principles that underpin, well, pretty much every modern AI system.
Okay, so for this deep dive, we're going to explore those key mathematical disciplines, how specific concepts apply in, say, emblematic AI algorithms like neural networks, and even acknowledge where the limits of our mathematical understanding currently lie. We're aiming to give you an accessible understanding of concepts like gradient descent and linear algebra within the context of AI, really linking the theory to the practice. Okay, let's unpack this.
Let's do it.
You might think of AI mainly as code, but at its heart, it's really a language of numbers and mathematical operations, isn't it? So where do we even begin with these foundational building blocks?
Well, we absolutely have to start with the bedrock, linear algebra. It's undeniably the native language of AI.
The native language.
Yeah, because it provides the fundamental structure to represent and, crucially, manipulate data. Everything from images to text, it all becomes numbers in the end.
Okay, so native language, what does that actually look like in practice? How does AI speak linear algebra?
Well, imagine any data input could be an image, a spoken word, maybe a sensor reading. Our sources tell us it's all transformed into a vector or, more often, a matrix of numbers.
A matrix, like a grid.
Exactly. Like a color image becomes a 3D matrix. You can think of it like stacking 3 transparencies, one each for red, green, and blue intensities. Each one is a grid of numbers representing brightness values. Combine them, you get your full color image. But the AI, it just sees this stack of numbers, this matrix, not really a picture like we do.
Got it. So it operates on those numbers.
Precisely. Then, the really crucial operations within a neural network, like those in what's called a dense or fully connected layer, are essentially matrix multiplications.
Okay.
Each layer applies a linear transformation and then, importantly, a nonlinear one to the data coming in. This is beautifully captured by that fundamental equation you often see, y equals x plus b.
Right, I've seen that. W is weights, X is input.
Exactly. W is a matrix of weights, X is the input vector, B is a vector of biases, sort of like adjustments, and that all-important nonlinear activation function.
Okay, you called all important. Why? What makes that nonlinear activation function so crucial? Sounds like a small detail.
That's a great question. It might seem small, but without this nonlinearity, neural networks would just be stacking linear transformations on top of each other.
That's bad.
Well, it's limiting. No matter how many layers you add, if they're all linear, you just end up with another linear output. Essentially, you've built a very complicated way to draw a straight line, metaphorically speaking. It's the nonlinearity that allows the network to learn these incredibly complex nonlinear relationships hidden in the data. That's what lets it recognize faces, understand speech, generate text, basically anything beyond very simple patterns.
That's a really powerful distinction, that linear versus nonlinear capability. And our deep dive sources really underscore this, don't they? They point out how techniques like singular value decomposition, or SVD, which is based on matrix factorization, it's fundamental to things like the recommendation systems we use literally every day.
Absolutely fundamental. By cleverly decomposing these, often massive matrices of user-item interactions, think movies you've watched or products you've bought, SVD uncovers hidden underlying patterns.
Like what kind of patterns?
Well, you can think of it as revealing latent features, things like hidden categories of user preferences, or maybe the inherent characteristics of products that aren't immediately obvious.
Okay.
And this allows the system to predict what you'll probably like, even if you haven't explicitly rated similar items before. That's how you get those. You might also like suggestions that are sometimes spookily accurate.
Right, the spooky accuracy. So, okay, if linear algebra gives us the language and the structure for the data, what's the actual engine? What makes AI learn from that data, adjust itself based on what it sees?
That would definitely be calculus, specifically differential calculus. That's the motor, really, that enables learning in machine learning. It's how models find their way, so to speak.
The motor. Okay, so how does calculus drive this learning process? I mean, finding the best way to adjust potentially millions of parameters sounds incredibly
Oh, it
complex.
is. And the core goal during model training is always to minimize something called a loss function, often written as J.
J theta,
Yeah,
right?
and that function basically quantifies the error, the difference between the model's predictions and, well, actual reality. Calculus gives us the tools for this minimization, primarily through partial derivatives.
Derivatives. Okay, calculus flashbacks.
Yeah. So the gradient, written as Shella, is essentially a vector. And this vector points in the direction of the steepest increase of that loss
The
function.
steepest uphill.
Exactly. So the gradient descent algorithm does the logical thing. It iteratively moves in the opposite direction of the gradient, essentially, the direction of steepest descent or downhill.
Ah, okay.
And it keeps taking small steps downhill until, hopefully, it finds the function's minimum point, thereby minimizing the prediction error.
That makes intuitive sense for finding like the bottom of one simple valley or curve. But what if the mountain range of errors is incredibly complex, loads of dips and bumps? Does gradient descent always find the true lowest point, the global minimum, or can it get stuck somewhere else?
That's a really critical challenge in practice. And yeah, it's something we'll definitely touch on more when we discuss optimization later. Basic gradient descent can get stuck in what we call local minima.
Okay, so not always perfect, but sticking with calculus for a moment, how does it connect all those layers in a deep network? You mentioned something ingenious, the chain rule.
Yes, the chain rule. It sounds so, I don't know, elementary from first-year calculus, right?
Yeah, pretty basic.
But it's precisely this rule that makes backpropagation possible in deep neural networks. And backpropagation was arguably the breakthrough that enabled modern deep learning.
Okay, why was it such a breakthrough? What did it solve?
Well, before backpropagation became efficient, training deep neural networks with many, many layers was computationally just prohibitive. It took way too long. Right. The chain rule provided this incredibly elegant and, more importantly, efficient way to calculate the impact or the contribution of each individual weight in every single layer on the overall final error.
Wow, okay. So it figures out who's responsible for the mistake.
Kind of, yeah. This responsibility for the error is then distributed or propagated backward through all the layers. That allows all the weights to be adjusted appropriately for learning, layer by layer, going backward from the output.
So it solved a massive computational bottleneck.
Exactly. It effectively unlocked the potential of deep learning that we see everywhere today. And this was technique really popularized and refined by researchers like Rumelhart, Hinton, and Williams back in the 80s and 90s.
Okay, fascinating stuff. But, the real world is messy. It's full of incomplete or noisy data, which introduces a lot of uncertainty. How does AI grapple with that uncertainty? It can't always have perfect data.
No, absolutely not. And that's where probability and statistics really come into play. They provide the essential framework for quantifying and managing that uncertainty, both in the data itself and within the model's predictions. It gives us a principled way to make educated guesses.
Educated guesses. How?
Well, one really key concept our sources highlight is Bayesian inference.
Bayesian.
Yeah, it's a way for models to continuously update their beliefs, which are represented as probabilities about something happening as new evidence or data comes in.
So it learns from new information dynamically.
Precisely. This is absolutely crucial in practical applications. Think about spam filtering, a classic example. As new emails arrive, the filter updates the probability that an incoming message is spam based on its content.
Oh,
It's also used heavily in medical diagnostics, updating the likelihood of a disease given test results, and even in robotics for something called SLAM, simultaneous localization and mapping, where a robot updates its map and its own location estimate as it moves around.
wow. Okay, so it's really fundamental for dealing with changing information.
Definitely. And beyond just inference, statistical metrics are completely indispensable for evaluating how well our models are actually doing.
Right, like accuracy.
Accuracy is one, but there are others like precision, recall, F1 score, and also things like p-values, which help us understand if our results are statistically significant, unlikely to be due to random chance,
P-values, right?
and confidence intervals, which give us a range where the true value likely lies. All these help us understand a model's performance, its significance, and crucially, its reliability.
And why is reliability so important?
Well, it's vital to avoid this common pitfall called overfitting. That's where a model gets too complex and
Hmm.
essentially memorizes the noise or the specific quirks in the training data, rather than truly learning the general underlying patterns.
Ah, so it performs great on the data it's seen, but fails on new stuff.
Exactly. It fails to generalize well to new, unseen data. Statistical evaluation helps us detect and prevent overfitting, ensuring our models are actually useful in the real world.
So these statistical tools aren't just for academic papers then. They're absolutely crucial for building AI systems that we can actually trust and rely on. Our sources pointed to foundational work like Thomas Bayes, but also modern developments like probabilistic graphical models.
Yes, PGMs. They are very powerful for representing complex probabilistic relationships between many variables. Really important for cutting-edge AI.
Okay, so beyond just handling uncertainty, how do we actually measure learning? Or maybe the goodness of a model's predictions, especially when it's trying to classify things into different categories?
That brings us neatly to information theory. This is a field largely developed by the brilliant Claude Shannon back in the mid-20th century.
Shannon, right. The father of information theory.
That's the one. It's a foundational field that lets us quantify concepts like information, but also uncertainty, and even impurity within data.
Impurity. How does that work?
Well, a key concept is entropy. In this context, entropy measures the amount of uncertainty, or you could say impurity, within a data set. High entropy means the data is very mixed up, unpredictable. Low entropy means it's more uniform or predictable.
Okay, that makes sense.
But perhaps even more crucial in modern AI, especially for training classifiers, is a related concept called cross-entropy.
Cross entropy. I hear that term a lot in machine learning.
You do, because it's a very, very common loss function, particularly in classification problems, figuring out if an image is a cat or a dog, for
Yeah.
instance.
Right.
What cross-entropy does is it measures the difference or the distance between two probability distributions. The distribution of probabilities predicted by the model for each category, and the actual true distribution, which is usually just 1 for the correct category and 0 for others.
So it compares the model's guess to the actual answer.
Exactly. Minimizing cross-entropy during training essentially forces the model to align its probability predictions with reality. It pushes the model to be more accurate and also more confident in its correct predictions.
Ah, okay. So if you're building that AI to distinguish between cats and dogs, minimizing cross entropy is what helps that model get its predictions as close to the truth 100% cat or 100% dog as possible.
Precisely. That makes it a core component for training models used in incredibly important applications, like computer vision,
Identifying objects.
yep, and natural language processing,
Understanding text.
like figuring out the sentiment of a sentence or classifying documents. It's fundamental.
Okay, so pulling all these mathematical threads together, linear algebra for structure, calculus for learning, probability for uncertainty, information theory for measuring predictions. Once we have all these tools, how do we actually find the best possible solution, the optimal set of parameters for an AI model, especially when there could be millions, even billions of them?
Right.
And critically, does that gradient descent method we talked about earlier always get us to the true best solution, the absolute minimum error, or just, a pretty good one?
Yeah, that's the million-dollar question, isn't it? And that brings us squarely into the realm of optimization. This is a whole branch of applied mathematics entirely focused on finding the minimum or maximum values of functions.
Okay.
And to your crucial point, no, basic gradient descent alone doesn't guarantee finding the absolute best solution, the global minimum, every single time, especially not in deep learning.
Why not?
Well, we need to understand this critical difference between convex and non-convex functions, or loss landscapes.
Convex and non-convex.
Think of a convex function like a simple bowl. It has only one minimum point at the very bottom. If you drop a ball anywhere inside, it will always roll down to that single lowest point. Optimizing convex functions is, relatively speaking, straightforward.
Okay, that sounds easy enough.
But the loss functions in deep neural networks are almost always highly non-convex. Imagine, instead, a vast, complex mountain range with countless valleys, peaks, plateaus, and saddle points.
Whoa, much harder to navigate.
Exactly. This makes the optimization landscape incredibly complex. There are multiple local minima valleys that are lower than the surrounding terrain, but not the absolute lowest point in the entire range.
Mhm.
There are also saddle points, which look like minima in some directions, but maxima in others.
So it's really easy for basic gradient descent, just following the steepest path down to get stuck in one of those local minima valley that feels like the bottom but isn't the actual lowest point overall.
Precisely. It's like a hiker trying to find the lowest point in a huge mountain range during a dense fog. You just keep feeling your way downhill, step by step, hoping you don't get trapped in a smaller dip high up on the mountainside.
That's a great analogy. So how do models avoid getting stuck? How do they try to find something closer to that true global optimum, the deepest valley in the whole range?
Yeah, for those of you out there who've actually tried training models, you know that simple vanilla gradient descent can be painfully slow. And yes, it often gets stuck. That's where much smarter, more advanced optimization algorithms come into the picture. You've probably heard names like ADAM or RMS prop, Adigrad.
Yes, definitely seen those.
These are sophisticated extensions of the basic gradient descent idea. They're specifically designed to navigate these incredibly intricate and complex error landscapes much more effectively.
How do they do that? What makes them smarter?
Well, they incorporate various tricks. For instance, some adapt the learning rate the size of the downhill steps for each parameter individually. Others incorporate momentum, kind of like giving the ball a push so it can roll out of shallow local minima and continue downhill. Some use information about the curvature of the landscape. They try different strategies to avoid getting trapped and to speed up convergence towards a good solution, even if it's not provably the absolute global minimum.
Okay, so they're like experienced hikers with better gear and maps for that foggy mountain range.
That's a good way to put it. And our deep dive material really highlights the ongoing challenges here. It points to foundational texts on convex optimization, which covers the easier bowl-shaped cases.
Right.
But as you said, the field is constantly evolving. Researchers are developing new algorithms all the time, specifically trying to tackle these incredibly difficult non-convex optimization problems that are characteristic of deep learning.
It's just abundantly clear from all of this that mathematics is, well, it really is the DNA of AI, isn't it?
Absolutely.
But despite its incredible power and sophistication, are there still significant challenges, areas where our current mathematical understanding kind of hits a wall when trying to explain or improve AI?
Oh, absolutely, yes.
Yeah.
Even with this profound mathematical scaffolding that we've been discussing, the relationship between the math and the resulting AI behavior still presents some really significant challenges that researchers are actively grappling with. It's definitely not a solved problem by any stretch.
Like what, for example?
Well, first, there's the notorious black box problem that comes up all the time.
The black box, meaning we don't know what's inside.
Sort of, but we actually do understand the equations inside a neural network. We can write them down. We can trace every single mathematical operation from input to output. That part is clear.
Okay.
But the internal reasoning, if you can call it that, or maybe the specific combination of abstract features that emerges from the complex interaction of millions or billions of these parameters, that is incredibly difficult for us humans to interpret or understand intuitively.
So the math tells us how the output is calculated, step by step, but not always why a specific decision was made, or why a particular neuron activates in response to some complex pattern.
Exactly that. We see the result, we know the mechanics, but the underlying semantic meaning of those intermediate calculations is often opaque. And this is precisely why the whole field of explainable AI, or XAI, is growing so rapidly. People are developing techniques to try and peer inside that black box and make the models more transparent and interpretable.
That makes sense. What other challenges are there?
Well, another fundamental one, rooted in statistics and widely discussed in our deep dive sources, is the classic bias-variance trade-off.
Bias variance. Right. Heard of that too.
Yeah, this is something pretty much every machine learning engineer or data scientist grapples with constantly when building models.
Can you break that down?
Sure. So an overly simple model, one that makes too many assumptions, might have high bias. It fails to capture the underlying complex patterns in the data. We call this underfitting. It's too simple for the job.
Okay, like using a straight line to fit a curve.
Exactly. Conversely, a model that's too complex, too flexible, might have high variance. This model can potentially fit the training data almost perfectly, but it does so by essentially memorizing the noise and the specific random fluctuations in that particular data set.
Ah, and that's the overfitting we talked about earlier.
Precisely. It fits the training data beautifully, but fails miserably when it sees new, unseen data because it learned the noise, not the signal.
So you have to balance the two.
You do. Mathematics provides the framework to understand this trade-off. We can measure bias and variance, but finding that sweet spot, that optimal balance between a model that's simple enough to generalize but complex enough to capture the true patterns. Well, in practice, that's often more of an art form guided by experimentation than a precise science dictated purely by equations.
Interesting. An art form based on math. What else?
Then there's the sheer computational complexity. This is a huge practical barrier. Many algorithms, even if they are mathematically sound, theoretically elegant, maybe even guaranteed to find the best solution, they might just be computationally unfeasible for the large-scale problems and massive data sets we deal with today.
Meaning they just take too long to run?
Way too long.
Mm.
Imagine trying to run a calculation that even on a supercomputer would take thousands of years. It's just not practical. So a lot of research actively focuses on finding clever approximations or heuristic sort of rules of thumb that maintain a good degree of mathematical rigor but are actually executable in a reasonable time frame on current hardware.
So finding mathematically good enough solutions that actually work in reality.
Pretty much, yeah. And finally, there's this really fascinating phenomenon of emergence. This is especially relevant with the huge models we see now, like large language models, LLMs.
Emergence? What emerges?
Well, the most advanced capabilities of these LLMs, things like complex chain of thought reasoning, surprisingly deep contextual understanding, even generating creative text or code, these abilities seem to emerge in quite non-trivial, often unexpected ways, simply from scaling up the number of parameters and the amount of training data massively.
So bigger models just suddenly get new skills.
It often appears that way.
Mm.
And our current mathematics still struggles to fully predict and explain how these incredibly complex, high-level cognitive-like properties emerge solely from the underlying, relatively simple mathematical components, the matrix multiplications, the activation functions, the gradient updates.
We know the building blocks, but we don't fully understand how they create the final structure's most impressive features.
That's a good way to put it. It's a major area of active, really groundbreaking research right now, trying to build a better mathematical theory of emergence in these large-scale systems. Truly a frontier.
Wow. That really highlights that even with this deep, sophisticated mathematical understanding that underpins absolutely everything in AI, there are still these vast frontiers of research and discovery ahead. It's clearly not just about applying what we already know, but really pushing the boundaries of what we can even comprehend mathematically.
Absolutely. It's an ongoing journey.
So what we've explored today, I think it truly shows that mathematics isn't just some useful tool for AI. It really is its fundamental DNA.
Couldn't agree more.
From the linear algebra that structures the data and defines the network operations, to the calculus that enables learning through gradient descent, the probability that handles the inherent uncertainty, and the information theory that helps us quantify it all, every single breakthrough in AI is, when you dig down, really an ingenious application of these abstract mathematical principles.
And comprehending this mathematical scaffolding, I think, is absolutely essential, not just for demystifying the technology, understanding how it works under the hood,
Right.
but also for fostering rigorous, responsible development of AI. It's also about educating that next generation of innovators, the people who can not only apply the existing models effectively, but who can also understand and actually improve their very foundations because they grasped the math.
That's a great point. So what does all this mean for you, our listener? Well, next time you interact with an AI, maybe it's a smart assistant on your phone, a recommendation engine suggesting movies, or perhaps one of these new creative writing tools.
Yeah.
Just take a moment and consider that behind its seemingly intelligent, maybe even slightly magical behavior, there's this whole universe of equations, transformations, probabilities, and optimizations hard at work.
Billions of calculations per second, potentially.
Exactly. It really makes you wonder, doesn't it, how much more profound will our understanding of that emergence phenomenon become as we continue to push these mathematical boundaries? And what new kinds of magic are we going to uncover as we do?
It's a fascinating question. The journey to understand intelligence, both the artificial kind we're building and, frankly, our own natural intelligence, is this ongoing dance with the numbers, with mathematics.
A dance with the numbers. I like that.
And the more we understand the language of that dance, the math, the more thoughtfully, the more effectively, and hopefully the more responsibly we can participate in it. Not just as passive users, but as informed explorers charting this new territory.